Today we are going to talk about performance-based design with protostructure. The topic is quite an extensive topic. Actually, it's difficult to talk about such a topic in 1 hour or 90 minutes. But what I will do is I will try to put some theoretical background. I'm sure most of you may be familiar with those. These are nothing but the basic earthquake engineering principles, but I tried to put them in a logical order so that we can understand what is a performance-based design and what kind of analysis and modeling techniques we are using. And at the end, if time permits, I will try to show you a quick example on how we approach to retrofit or assessment in protostructure. So let's get started. I don't want to lose any time because it's very valuable. We have lots of topics to cover. So I will briefly talk about Prota Group, and then I will talk about the performance-based design. So Prota was founded in 1985. We are now a leading global software company. We are specialized in engineering and consultancy as well as software development. Prota Group is now a leading software company together with engineering and consultancy group. We comprise of 6 companies. I'm here representing Prota Software. In fact, we are the developers of the engineering software, which is called Prota Structure. Prota Computer is the reseller, largest Autodesk reseller in Turkey. In fact, we are a platinum partner now. We have over 70 employees, and we are the biggest partner in Middle East and Eastern Europe, including Turkey. So we are also a direct provider and trusted advisor of BIM solutions, including AutoCAD, Revit, Civil 3D, all the mechanical portfolio of Autodesk, Prota Structure, and Adobe. Prota Engineering is the second company of Prota Group. It's the largest and most prestigious engineering and consultancy firm in Middle East region. We have completed more than 1,000 projects around the world. Now we are an expanding company and we are growing every year. Today we operate with more than 15 offices located in Malaysia, Singapore, Philippines, Poland, and Turkey. We are planning to open up another office in Berlin, Germany in 2020 if the pandemic goes well. So we are planning to extend our services in Western Europe as well. So besides our regional offices, we support our customers and provide services through our channel partners. We have 16 partners in Europe, Africa, Middle East, South America, and Southeast Asia. A quick summary of our journey in a timeline. We were established in 1985. Our first software technology, Orion, started being distributed in 1995. In 2000, we have become a global software business. And in 2008, we have introduced first BIM links with Autodesk Revit. In 2013, Prota Asia was opened to give direct support and training to our clients in Southeast Asia. In 2018, we introduced our steel detailing module, Prota Steel, which is very powerful software. And lastly, in 2019, we launched our Europe headquarters in Warsaw, Poland, Prota Polska. Some of the quick field of services for Prota Engineering can be the building design, transportation, industrial energy, high-rise buildings. Also, we are specialized in design and consultancy in earthquake and seismology fields, historical structures, construction management, BIM technology, and planning. Here are some Prota Engineering important projects around the world. So recently we have been heavily involved with airport design. We designed the Istanbul New Airport, which is the largest airport at the moment. Also, we are specialized in seismically isolated buildings, and we have been heavily involved with metro projects all around the world. So Prota Software is the software developer company. As I said, we are developing the Prota structure, which is the ultimate solution for modeling, analysis, and design of structures. Prota Details is for your automated detail drawings, reinforced concrete drawings. It includes intelligent rebars and design libraries, such as retaining wall, scaffold design, detailing, pile caps, pool design, and all the design and detailing libraries that you can use independent of your structures. Prota Steel is our latest technology for your steel detailing and connection design. We have shop drawings and general arrangement drawings, as well as connection design reports. And Prota Beam is our beam tool, which allows you to bidirectionally link your models with other beam platforms, including Autodesk Revit. We also support, with the upcoming 2020 version, we will support IFC import, and also we will support imports of 3D DXF files. We already support the import of two-dimensional DXF files. So Prota Structure is the focused structural beam design solution of Prota. Some of the capabilities are flexible 2D and 3D modeling, multi-material modeling and with physical objects, analysis and detailed design to international and seismic and design codes. Also, we provide full design reporting and quantity takeoff. So in a nutshell, the main core competencies of Prota Structure is the ease of use, fast modeling, and maximum productivity. What's our biggest advantage? As Prota, our biggest advantage compared to other solutions on the market is that we offer a comprehensive solution for our clients. With Prota Structure, you can design model buildings, then perform automated steel and reinforced concrete detailing with Prota Steel and Prota Details platforms. You can also coordinate your models with leading beam players with Prota Beam. In other words, you invest in a single package and you possess all these technologies. And from time to time, we are demonstrating these technologies throughout seminars or webinars. But today, as I promised, we will be discussing the performance-based design, in which Prota Structure is quite powerful. So let's jump into performance-based design. So as you know, we have different design paradigms in terms of earthquake-resistant design. The conventional design paradigm is what we do. We design the buildings under a design earthquake, which is usually the earthquake which has 10% of probability of exceedance in 50 years. In other words, it will have a return period of 475 years. What we do, we design for strength under the reduced earthquake loads. So we are trying to make sure that members are strong enough to withstand the demanded forces, and inertia forces are safely transferred to load-bearing system, like diaphragms or collectors. And while doing that, we also try to ensure that structure has the required ductility capacity. What does it mean? It should be deforming. It should be able to deform in the plastic region without losing significant capacity. And while doing that, we try to prevent brittle failure. We try to prevent undesired collapse mechanisms like story mechanism or loss of equilibrium. And we achieve that by providing sufficient ductile detailing. So you can see this in this graph. It is nothing but the equal. It explains the equal displacement rule. So you can also simulate this with a single degree of freedom system effect. So if the structure was to behave elastically, we would have the elastic strength, which is Fe. But the structure, of course, behaves in a nonlinear manner. So we have a yield strength of Fy, which is nothing but the elastic strength divided by the yield strength reduction factor, which is Ry. But we also have a design strength because we have material discrepancies. Materials can be stronger than we expect, or we may have more provided reinforcement inside the members. So always, as built structure may be more strong than we anticipated. So we also cover that by an overstrength factor, which is Fy divided by D. So this is pretty much the conventional design approach. What we do, we calculate the elastic strength demand. We assume a ductility capacity depending on the structural type and the building. And of course, we calculate, we prescribe some reduction factor, which is called R, and we prescribe some overstrength factor. And by reducing the elastic demand, we design the structure under the design earthquake. Then we provide sufficient detailing to ensure the ductility. That's the conventional approach. But why do we need performance-based design? I want to ask some questions. So as I said, we usually design under design earthquake of with a return period of 475 years. So what happens? We have an earthquake, a severe earthquake with a return period of 2,000 years, or if we have a very frequent earthquake with return period of 73 or 72 years. So what kind of performance do we expect from the building? Other question can be, what kind of damage is tolerable for us? No damage to structural and non-structural members, limited damage, heavy damage but not collapse. What is our tolerable damage? And also, what is the cost that we can tolerate to repair the building after damage? Okay, the conventional design philosophy tries to ensure the life safety of the building, life safety of the mankind, people living in the building, but building can be damaged. But because of economical considerations, this damage must be repaired. So what kind of cost can we tolerate to repair the building? So if the building is out of service after a catastrophic event, what is the cost of out of service scenario? And what is the occupancy type of building? So is it an emergency building like a hospital or a data center or other type of industrial or power plants? Depending on the building occupancy, can we afford the out of service scenario? And lastly, other than necessities or other code requirements, what does our client expect? Because we are engineers and we are serving some clients, of course. So if the client has money, they can expect an advanced performance scenario. So a client may not want to even wake up when the earthquake happens. So these are the questions that leads to performance-based design. So for the performance assessment, we have the two phases of the medallion. In fact, for new buildings, if we are requested to design a new building with performance-based design, our job is relatively easy because we are in control of architectural and structural design. Building is new. We are in control of materials that we will use. We decide on the budgets versus expected performance. And we can also fine-tune the system by using seismic devices like isolators, viscous dampers, and so on. So for new buildings, performance-based design will allow us to consider these items. But for existing buildings, we work with existing material and structural system. We may have existing damages to structural members, which is very critical. They may be repaired or they may be beyond repair. So there is an unknown factor, or if we didn't do any sufficient survey in the building, we may have missed out these damages as well. The architectural function is important. While retrofitting the existing building, you must not prevent architectural usage too much. So we must be careful with the architectural function as well. So that's another difficulty in existing building. Also, cost of retrofit versus tear down is an important factor. Usually up to 25% is acceptable. So if you are going to tear down the building and rebuild it again, if the retrofit cost is not exceeding 20-25%, it can be acceptable, but more than that should be considered. So after assessing the performance of an existing building, we decide on retrofitting the building or tearing it down. So there are more unknowns and more parameters out of our control in existing buildings. I want to talk about analysis approach while we are designing the buildings against earthquakes. So, of course, the simplest approach is the linear elastic analysis. And the members, the finite element members that we use in linear elastic analysis are also assumed to be linearly elastic. So force deformation relations are constant. That brings us ease in modeling and less computational effort. But of course, in terms of nonlinearity and performance assessment, linear elastic behavior is not so accurate because it doesn't have any damage memory. It doesn't behave non-linearly. So, although simplest approach, not so accurate for performance assessment purposes. It's quite acceptable for conventional design, as I explained before. The alternative is the nonlinear elements and nonlinear analysis. So when we use nonlinear elements, what we mean is the force deformation relationship is dependent on the deformation level. So the stiffness is changing. Also, it requires complex modeling and it requires more computational effort. It's more realistic. And also, as the nonlinear force deformation means a representation of damage. So nonlinear approaches are more accurate in terms of performance assessment. So for conventional design, what we use as linear elastic analysis is, first of all, the simplest one is equivalent static method. Equivalent static method, of course, does not consider the effect of higher modes. That's the most important drawback of this static force approach. It does not consider higher mode effects. It's usually valid for relatively regular buildings with high mass participation. But since it is approximate, seismic codes are applying penalties to that. If you have floor torsion, you have to increase the accidental eccentricities. If you have weak stories or soft stories, you have to change behavior factor or you have to change your method of analysis. So it's simplest, but it's the most approximate approach. The other approach for linear elastic analysis is response spectrum analysis. It's a good approximation, actually. But still, it assumes that the modes are independent. It assumes no mode coupling between the modes, and also it's based on calculating the pseudo responses of undamped modes. So, but for linear elastic systems, it's quite good and quite good approximation. But there are some disadvantages. One of them is after SRSS or CQC combination, we lose the force displacement signs, and of course we lose the equilibrium. Although we calculate the base shear, we have to scale the base shear up to static base shear level. That's another thing that we have to do. Another disadvantage or the point that we must pay attention is the mass participation. It's an issue. If we don't select the sufficient number of modes, then higher mode effects can be skipped. And for conventional design, other things that we use are the code spectrum or site-specific spectrum for weak soil conditions. If you like, you can consider geometric nonlinearity in the design. What I mean by geometric nonlinearity is the p-delta effects or second-order effects. And also, conventional design or linear elastic approaches can be used as a starting point for performance-based design. Because as you would appreciate, nonlinear assessment requires the section sizes and the rebars, the reinforcements, to be available as an input. So that means we have to do a preliminary design first. So as a starting point, you can use the conventional design approaches for the preliminary design for performance-based approaches. So for performance-based design or assessment, what kind of analysis methods do we have? First of all, we have linear elastic assessment methods. In the literature, researchers always tend to invent new methodologies or easy methodologies that everyday engineer or practicing engineer can make use of efficiently, because as the analysis methods get complex, the computational effort and assumptions and the parameters get more rigorous and difficult. So the simpler the methods, the easier to use. It's easier to use by practicing engineers. So one of the methods that's quite easy to implement is the linear elastic assessment method. In this assessment method, what we do is we perform an equivalent static or RSA analysis, like in conventional design. But in this case, we assume that the reduction factor is 1. We don't reduce the elastic demand. We assume that the building is not important. The importance factor is 1. And the additional eccentricity is 1. So we normalize the building. We don't assume any ductility. We don't assume any additional eccentricity. And we use the elastic conventional design to calculate the elastic responses. Then the plastic demand is approximately calculated from elastic chord rotations. While doing that, we calculate the material nonlinearities separately. And then we compare these calculated responses with the code specified parameters. Of course, what are the disadvantages? Of course, this method is approximate and very conservative because it's based on a linear elastic analysis. It's considered to be approximate. A conservatism comes from this approximation because penalties are applied. So also this method does not consider the hinge mechanism and redistribution, but it's simple to apply, and it's only valid for certain type of buildings. Another widely used method of analysis is static pushover analysis. Simply, what we do, we incrementally load the structure until it is not stable. While pushing it in X or Y direction, simply we plot the base shear versus roof displacement. Then we convert that shear versus displacement graph to and spectral acceleration into spectral acceleration and spectral displacement domain. And we compare it with the target spectrum, and we try to find the demand that the earthquake demands from the structure. In this analysis, material nonlinearities are considered, of course, in the critical sections that we expect the highest demand. But one serious disadvantage or drawback is the lateral load vector. Since we push it with a certain type of load vector incrementally, the shape of that load vector is affecting the results a lot. Some of the alternatives are a constant loads, inverse triangular loads, the shape of the first modes, etc. And usually we use the first mode, but the ideal shape is the nonlinear deformed shape. But we don't know the nonlinear deformed shape from the beginning. And that's one of the drawbacks. And also it's also what we call a single mode static pushover, so it doesn't include the effect of higher modes as well. But the capacity curve we obtain at the end of the analysis is a generic curve. It's independent of the demand. If you match the curve with any demand, you can assess the structure as you like. As I said, the static pushover, single mode static pushover is quite considered also an approximate method because of the higher mode effects. In fact, it is not applicable for buildings more than 8 or 10 stories, or buildings which have participation factors less than 70% mass participation, or buildings which have high extreme floor torsion situations. This static pushover will not be applicable. So in the literature, we have other methods like multi-mode pushover analysis. But unfortunately, in this field, there are multiple approaches. The main problem is the superposition problem. So since most of the methods assume that the model coupling is ignored, usually, we cannot go back and superpose the nonlinear system. We cannot just combine them with CQC or SRSS. That's the main drawback. But of course, there are several publications, several methods developed. They either combine the loading first, or after loading, they either combine response, or they do a serious pushover analysis and they combine the results. But unfortunately, there isn't a widely accepted method currently available. The static pushover, unlike multimode, static pushover is used for a very long time, and it's somewhat generally accepted, but we don't have any widely accepted method for multi-mode pushover analysis. And also there are no recommendations on that. And finally, we have the nonlinear time history analysis. So this analysis, of course, is considered to be the benchmark in the prediction of response. What we have is we have an accelerogram, a ground motion record, and by using the dynamic equilibrium equations, we apply this acceleration to the building with direct integration or model response history methods. But in this case, since the accelerations are both negative and positive, we need hysteretic material definitions. So that's one important thing. Also, if you remember the dynamic equilibrium equation, we have acceleration, which is multiplied with mass. We have displacement, which is multiplied with stiffness matrix, and we have the one derivative of acceleration, the speed, which is multiplied with damping matrix. But as you know, damping is not a very, how to say, easy parameter to obtain. So what we do, we usually assume 5% critical damping for reinforced concrete structures, but it's just an assumption. It's during the earthquake, because of the cracks that happen in the concrete or damages, we assume that approximately there's a 5% damping. And one of the important things that we need to pay attention in nonlinear time history is the damping factor. We need a damping matrix that is proportional to mass and stiffness for the numerical computation, and that's called the Rayleigh damping. But it can severely affect the response if you overassume the damping, though your responses will be low. If you underestimate the damping, then your responses will be very high. So you should be very careful about that. And another important parameter for nonlinear time history is the ground motion selection, because the major input in this analysis is the accelerogram, and you have to select the ground motions very properly. So depending on the project site that your building is located, you must go to the peer database or other ground motion databases, and you must select the proper ground motions in terms of magnitude, similarity in terms of magnitude, fault mechanism, which can be normal fault, reverse fault, or strike slip fault, and distance to fault. So after selecting these ground motions, you have to scale them. You cannot just use the ground motions as you download from the database. You have to scale them to the code specified spectrum between a short period and a long period interval. It's usually 0.2 times t and 1.5 times t. And depending on the seismic code, you must scale it to the level of earthquake spectrum, elastic spectrum. But that's not finished. After you process your ground motions, you must use 3 to 11 ground motions. You cannot just use one ground motion. You are not allowed to do that. You have to use 3 to 11 motions, and at the end of the analysis, you must calculate their maximum or average responses. And also, you cannot apply a ground motion in one direction only. You must apply 2 ground motions simultaneously in X and Y direction. So if you apply the yellow ground motion on the screen in X and green ground motion in Y direction, in another analysis, you have to rotate the axis by 90 degrees and apply the yellow to the up in Y direction and apply the green in negative X direction. So that means your post-processing effort now is multiplied by 2. So as a consequence, we can say that post-processing of nonlinear time history is quite tedious. Also, analysis itself is computationally very expensive because equilibrium must be satisfied at each time step with material nonlinearity, because we assume that we have distributed or lumped plasticity at the critical sections. And also, if you include geometric nonlinearity like P delta, you have to also iterate for those as well. So it's a very complicated and computationally expensive analysis. So what about these were pretty much the nonlinear analysis methods. As you are aware, I am not showing anything in protostructure because performance-based design topic is quite theoretical, and in order to proceed with the computer software, we must understand the underlying theory and underlying analysis and modeling approach very clearly, so that I'm emphasizing this today. I'm sorry if it is a bit boring for you. I'm not sure. At this point, I want to just check. Do you have any complaints about the conduct of the webinar? What do you think? Do you like how I go? Great. If you have any feedback, please ask through the questions pane. I'm happy that you are happy with the presentation. So these were the pretty much analysis techniques that we use. But what about the nonlinear behavior? How do we model the nonlinear behavior in the analysis? So all these pictures, you see some sort of damage in the structural members. So and deformation characteristics. The numerical methods we use must be proficient enough to reflect these damage models and energy dissipation characteristics to the model itself. Usually, these damage models, stiffness and energy characteristics are calculated from experiments, and models, material models, and nonlinear models are developed. So these must be reflected to our simulation models. What we do with the software is, of course, simulation. So we have as I said, we have a material nonlinearity occurs when stress-strain or force deformation relationship is nonlinear. So that's what we call a material nonlinearity. A geometric nonlinearity is different. The material can be linear, but because of the geometry or imperfection or the dimension of the structure, we may have second-order effects like P small delta or P large delta. Then we will have unexpected moments, unexpected increased internal forces due to these imperfections or simply geometric characteristics. So this is what we call geometric nonlinearity. And what about the material nonlinearity? If you forget about geometrical nonlinearity at the moment, for material nonlinearity, what we use usually, one of the methods we use is the lumped plasticity. In this approach, beam column elements are elastic and rotational springs are defined at the end of the element nodes. So at the critical sections, we have two rotational springs, which are assigned, of course, some stiffness characteristics compatible with the material properties. But the beam column element in between is elastic. The advantage of this is it's quite simple. It's not computationally very difficult. And it can be preferred in the interface effects like shear sliding or rebar slip because the output it gives is a plastic rotation. So you can compare this plastic rotation value with the plastic rotation limits that you obtain from experiments, for example. In a certain experiment, you may have a plastic rotation limit that also includes a rebar slippage factor, etc. So the macro output, the plastic rotation is quite useful, but it has disadvantages, of course. Rotational spring properties depend on geometry and moment distribution. We need a plastic hinge length. We need to estimate the extent of the nonlinearity in the critical section, but it's usually taken as the dimension over 2. But most importantly, as you know, especially in column elements, we have an axial load moment interaction. So we cannot really explicitly simulate or reflect the axial load moment interaction in lumped plasticity models. What we supply to the software is the moment rotation relationships, and we also supply interaction relationships. And when the critical section reaches its capacity, we try to stay on the interaction curve so that we can honor the axial loads moment relation. The other approach we have is the distributed plasticity. Unlike lumped plasticity, the distributed plasticity allows the yield occur at any location along the element, and it spreads the plastic behavior. It's computationally complex, but it's accurate, especially when we have highly changing loads and we expect high nonlinearity. In this picture, you see different modeling approaches like concentrated and distributed plasticity. The state-of-the-art approach at the moment is to use the fiber sections. What you do is you just mesh the concrete section together with the confined and unconfined concrete and the steel bars. And by using these fibers, you obtain you connect these section stiffness matrices to building stiffness matrices. That's the most advanced approach. But other than that, by using this fiber analysis, you can obtain the force deformation relationship and assign them to the plastic hinges as well. That's another approach. But what we do in protostructure is we use distributed plasticity. We use the finite length zone approach. It is not a fully distributed plasticity. It's actually a trade-off for simplicity. It's not fully nonlinear. Nonlinearity is confined to the end regions. We expect the highest demands at the end, so we use the distributed plasticity in 6 integration points in these confined regions, and the element in between is a linear elastic element. So we can maybe talk about other modeling considerations. Let me check the questions a little bit. Time history analysis can be done in Prota, but one of the questions is about time history analysis. It's asking if time history can be done in protostructure. We can do it with the help of protostructure OpenSeas integration. We have an OpenSeas integration feature. So we prepare data for OpenSeas, and we allow OpenSeas to perform the time history analysis, nonlinear time history analysis. Okay, let's continue. So what about the other modeling considerations? So up to now, we all talked about the frame members. We didn't talk about shell members a lot. So what if we want to model the material nonlinearity for shell elements, especially for walls? Unfortunately, there is a limited literature on that. You can successfully model the material nonlinearity of shells using the continuum models in software like ANSYS or Abacus. But it may not be really practical to adapt it to a structural engineering software to be used in a time history analysis, maybe. And also there are other approaches like multi-layer shell elements. It's also experimental and not widely accepted. And these nonlinear shell approach models are complicated and they require more effort in analysis. So one of the questions is it worth it? The other question is, are they accurate enough? So I prefer to put a question mark here regarding this topic. So other modeling consideration is slabs. Of course, in a performance assessment or an existing building assessment, you can mesh the slabs. You can use them for load distribution, and you can, if you want to allow flexible diaphragm approach, you can use them. But mostly we don't expect any nonlinearity in the slabs. we use them for load distribution and diaphragm assumption. So I want to put a question mark here. Is it really worth including the slabs as meshed in the performance analysis? That's a question mark. But if the building allows, if you use rigid diaphragm approach, it will bring simplicity to computation and computational ease. And also, we are facing lots of convergence issues, especially in nonlinear time history analysis. So simpler the model, the less the convergence issues we will face. And also slab effects are also presented by diaphragm action. And you can also distribute the loads with yield lines. You don't have to mesh for the load distribution. Of course, these remarks are only applicable if your building is permitting this. If you have a highly irregular building with gallery openings or separate diaphragms or the slabs that cannot act as a rigid diaphragm, then of course you will have to use slabs as finite element mesh. What about the non-structural members? In the buildings, of course, we will have partition walls and machinery. What we usually do, we include their loads and we calculate it during the design. And during the modeling, we act on the structural members. But in performance assessments, if you desire, you can model the infill walls with simple approaches. You can include them as compression-only composite strut and tie models. So if you push the building from one direction, the compression members will be active. If you push the frame in the other direction, then the compression will be reversed. So you will need to spend some effort in doing that. But the question is, of course, is it really worth it? So I also want to put a question mark here. So because people usually tend to model everything in the building, and but at the end of the day, the results may not be accurate, or it may not worth the effort. Another question mark I want to put here is the soil structure interaction. So what can we do if we expect a nonlinear soil behavior, and what if we have piles and pile groups under the building? How will we model the lateral pile supports, the effect of the soil to the piles and to the upper structure? These are all big question marks, really big question marks. So after we talk about this modeling approach and analysis approach, what we do for performance-based design? Okay, what is the essence of the thing? For performance-based design, we want to reach a target performance. For example, if I may give some examples from the Turkish earthquake code, for new buildings, we have regular performance targets and advanced performance targets. So if you pay attention, regular performance target is nothing but a controlled damage. It means the building should be satisfying life safety requirements with repairable damage. And the method we utilize is the strength design. So when we apply the code clauses and code equations under the design earthquake with a 500 years return period, then this condition is satisfied. But what if we have a different building? If we have a critical seismic design category, which means the building is higher than 60 meters, we are experiencing high spectral accelerations, and the building has an important occupancy time, then we have to satisfy three different performance levels simultaneously. So for the design earthquake, the performance target is the same. We utilize strength design, and we must satisfy the controlled damage criteria. And also, we can use this as a preliminary design for other performance approaches. So for a more frequent earthquake, like with a return period of 72 years, we must satisfy the limited damage criteria, but we must use a displacement-based approach. Now we cannot use any linear elastic analysis. We must use a pushover or time history analysis, and we must satisfy limited damage. So limited damage criteria is a bit more tighter than strict than the controlled damage criteria. And also for a severe earthquake, we must satisfy controlled damage as well. But we must utilize a nonlinear displacement-based analysis. The same thing is also valid for high-rise buildings. Design of high-rise buildings is a bit different in Turkish earthquake codes. We have more performance targets. So, for example, for a more frequent earthquake with a return period of 40 years, we can do a strength design, but we must satisfy the uninterrupted usage. That means ignorable or no damage. For a design earthquake with a probability of exceedance of 10% in 50 years, we can use strength design, but we must satisfy the controlled damage criteria. It's also a basis for preliminary design. And also simultaneously, we must satisfy the collapse prevention in a severe earthquake, but we must use a displacement-based approach. And existing buildings are similar, so we must satisfy. First of all, for existing buildings, we cannot use any strength design because the building is existing. We cannot assume any ductility. We cannot attach any ductility to the building, so we must use a displacement-based assessment, and we must satisfy these conditions. So why I gave you these tables, because I think it's very important to understand this if we want to understand performance-based design. So unlike the strength design, when we start the project, we have to look at these tables and we have to understand what kind of performance criteria I should be satisfying for my project. That has to be defined, that has to be decided before starting the project. And the analysis methods are dictated or recommended by the guidelines or by the codes. And usually for the assessment of the buildings, a peer review is required by the Turkish codes, as a side note. And of course, after setting these targets, what we do is we check the members if they satisfy the target performance. For example, if we are using lumped plasticity models, we have to use the plastic rotation limits. For collapse prevention, we have a plastic rotation limit calculated with a formula. And for controlled damage, the limit is 75% of this plastic rotation. And for limited damage, of course, we don't expect any plastic rotation in the members. Of course, what we do, we just classify the members according to this, and we reach a conclusion. So if the building itself satisfies the performance or not, we simply count the members. Of course, meanwhile, the brittle failure is not allowed, and additional drift limitations apply. The plastic rotation limits may be satisfied, but a building may be violating some drift limitations. That's another thing. If you are using a distributed plasticity, then we must now compare the concrete strains and the steel strains, most critical concrete strain and most extreme steel strain. So also these limits are given in the codes or in the guidelines. You have to, for each member, you have to satisfy these limits. So you count the members again and classify accordingly. Again, the brittle failure and drift limitations must be paid attention. So this is pretty much the theoretical part that I want to cover. I hope I could explain it to my knowledge. Now I will briefly show an example in protostructure. I will try to assess a typical school building. It's a 3-story frame structure with 14 megapascal of existing material and concretes and 220 megapascal existing reinforcement. Actually, these kind of schools are very very common in Turkey. Before the 1997, 1999, and we had lots of these school buildings, and we, as Prota, we also retrofitted lots of these school buildings. So let's continue. Let me check the questions a bit. Is there a buckling analysis in Prota? No, what we utilize is P small delta analysis for small deflections. And also, while designing the columns, we are using the short column approach. So what we use is the amplification of the moments. Yeah. Okay. We already spent 1 hour. Let me continue with my example. So this is a typical school building. What I did, I just modeled this building as I were modeling a new building. It doesn't matter. But what I did is I just using the material definitions here, edit materials. I just changed the existing material. After the survey, you have to enter the existing material using edit materials menu. You must change the default material. So default material is 14 megapascal concrete. If you have different default materials for different stories, you can also add them here. But I won't spend too much time on giving tutorial on these menus. Also, you can change the rebar grade here. So as a result of surveys or blueprints of the building, we see that the columns, longitudinal bars are and links have a characteristic yield strength of 220 megapascal. Okay, so this is the existing material. And we have the existing geometry already defined in the building. At this point, what is missing is the existing reinforcement. If you have the blueprints of the building, what you can do is you can just go to the column design menu, double click, and without doing any design, you can change the rebars. Okay, and you can set the links, like in the span region I have V8/20, and in the support region I have V8/15, very minor or no confinement as well. Maybe it could be the case. Some of the buildings do not have any confinement in their support regions of columns. So what you can do, you can just enter the reinforcement information and hit OK. You don't have to satisfy the design status here. All you need to do is to enter reinforcement information. This design status can be a red cross. We are not aiming to design the column. We are just aiming to enter the existing reinforcement information. That's what we want to do. So that's why I only enter the reinforcements, longitudinal bars, and links, and I press OK. I don't care whether it is green or cross. This is useful. If you have similar columns, you can copy and paste to all columns. But this is what you can do if you have blueprints available. Sometimes we don't have the blueprints of the building available. And as a result of the survey, you may have some estimated reinforcements. You can also define those in the assessment menu. What I will do, I will just go to Analysis and Building Assessment menu. So here in this menu, first of all, I have to select my analysis method. I want to do a pushover analysis. This is just preparing the analysis model first in order to set some initial parameters for pushover. Okay. Then I need to set the building information level. Depending on the level of survey you did in the building, you may have a detailed information. Detailed information means you did a detailed survey plus you have the blueprints of the building. If you don't have the blueprints, you will definitely have a limited knowledge. And if you have other custom information level, you can just change the factor here. This factor is used to decrease the member capacities. That's how we use it. Sorry, there are children outside shouting. And in the table below, we have performance. I already explained the performance. What's performance? What kind of performance goal we want to achieve under what kind of earthquake level. So here DD2 is a notation from Turkish earthquake code, but it means a design earthquake. So under the design earthquake, 10% of exceedance in 50 years, we will try to satisfy controlled damage. By checking these options, you can try to satisfy multiple performance criteria at once. But I will not just care about the rest. I will just concentrate on this performance level. As I said, if you don't have the blueprints of the building, you can use the approximate steel. Because when you survey the building, what you do, you just break some concrete covers. You just if you have 20 columns in one story, maybe you break the concrete cover of 2 or 3 columns or 4 columns or beams as well, and you generalize that knowledge. You assume that every column in the building is approximately has this amount of reinforcement with this amount of links. And also for beams, you can use the estimated or approximate steel amount. Okay. After I set these parameters, I will go to the pushover. I will set the pushover parameters here. I will have a 200-step pushover. I will push the building in X direction. Which node I want to monitor is this diaphragm master joint at the third story, which is D31. And I want to push the building up to 0.15 centimeters. Let's do the analysis. What we are doing now is we are creating the force deformation relation of the members. We are using the fiber discretization under the hood. And it says performance goals failure. We cannot satisfy the performance goals. We have the pushover curve calculated like this. I will, at the end of this exercise, I will have just a couple of slides about these curves and the reports. If you check the report, we will investigate the reason of the failure. Okay, first of all, the controlled damage criteria is not met. Performance level is collapse. When we check the member failure type table, first of all, we classify the members according to their failure types. We don't have any brittle members, but number of vertical members, the percentage of vertical members or columns or shear walls. We don't have any shear walls, but percentage of columns in the failure region is 33%. It's exceeding 30%. So that's why the performance criteria is not met. That means we have to do a retrofit operation here. But our first consideration must be to improve the structural system. There are two tendencies here. Engineers usually tend to put column jackets in the failing members, so they want to just how to say repair them or improve their performance individually. But if you want to cure the building, instead of removing the symptoms, you have to cure the disease. So we have to improve the structural system instead of trying to put column jackets to each and every column that we see which are failing. We have to improve the structural system. Maybe because of the lateral deformation, the building is suffering a lot. So if we can limit the lateral deformation, and if we can increase the lateral strength, then maybe the building can be retrofitted quite good. So what the strategy I will apply here is, I can show in another model. What I did, at these frames, I introduced these retrofit walls. If you check their properties, the wall model is the retrofit wall model, and also their material is C30, 30 megapascal compressive strength with a 420 megapascal yield strength in reinforcement. So these walls are not using the default materials. Default material was, remember, 14 megapascal, but these walls are new, and these are using new materials. But again, the question is, okay, what I try to do is I try to put the walls in a symmetrical manner so that I don't introduce any accidental torsion to the building, because I don't want to disrupt the load distribution. Otherwise, I may make it worse by introducing unsymmetrical retrofitting members. Anyway, so first of all, I need to select a reinforcement. I need to estimate the reinforcements inside the retrofit walls. And for that purpose, what I do is I just go to seismic parameters. I just assume that the ductility factor is 4. It's just a preliminary design. I want to put some initial reinforcement to the retrofit walls. So for that purpose, I am selecting the behavior factor as 4. And I'm analyzing the building. I want to emphasize again, for the existing buildings in Prota structure, my purpose is not to design the building. I want to put some reinforcement in it. It can be the existing reinforcement, or it can be a preliminary reinforcement for retrofit members. And I want to assess their performance. I will not be interested in their design status, whether they are okay or not. Their status will be dictated by the performance. Okay, close. And again, I will go to the column design menu. In the column design menu, if I filter the walls only, so before the webinar, I had already selected some reinforcement in it. Let's say 14. Okay. In fact, you can do a batch design. Let's do that. Okay. What I did, I analyzed the building with a behavior factor of 4. I assumed a very limited ductility for the building. And for the preliminary design purposes, I selected some preliminary reinforcement inside the retrofitting walls. And I go to and I double click on one of the walls and check the shear design. So maybe I can select a 14 bar in the web region, and OK, and copy and paste to all the walls. But if you pay attention, when I double click this, it's a retrofit wall. So we have an extra button here, which is called dowel design. You can also design the dowels, because these retrofit walls will be installed between the existing frame. You will not just tear down the existing beam or existing columns. Okay, you will just put the wall in between these existing beams and columns. So that means you will have to introduce some anchorages or dowels inside this existing frame. So these dowels can be calculated by Prota structure as well. So here you see number of top dowels, left dowels, right dowels. All of them are designed. It's nothing but a friction shear check, okay? Because we have a shear force acting at the beam wall interface. And also we have constrictive dowels here. So this design is done. And also in Prota details, you can get the detailed drawings for these dowels as well. Okay, let's say cancel. So now I have existing reinforcement. I have a preliminary reinforcement in the retrofit walls. All I have to do is go to analysis, building assessment. After this, the operation becomes a repetitive operation because now I select pushover again. Then we will create the analysis model for the pushover. What we do is we just analyze the building once more with behavior factor 1, importance factor 1, and eccentricity 1, and we prepare the building for pushover analysis. So that's what we are doing at the moment. Okay, we have existing reinforcement in the columns and beams. We have reinforcements, preliminary reinforcement in the retrofit walls. Let's go to pushover parameters. Again, I'm doing the analysis in X direction, and I will push the building up to 0.012 meters. And let's see, that's pretty much the demand displacement. So again, we are preparing the force deformation relationships using the existing reinforcement. Now the performance goals are satisfied. With this retrofit scheme, I could satisfy the performance goals. This is the pushover curve that I have here. So let's go back to the slides. So this was the retrofit layouts that I proposed. I used 30 megapascal and 420 megapascal steel and concrete. This is the comparison of pushover curves. The blue one is the retrofitted structure, and the orange one is the existing structure. It is the base shear versus displacement curve. But in order to find the demand, we have to convert this pushover curve to spectral domain in ADRS format. So the blue one you see is the blue curve you see is the code spectrum. Orange one is the retrofitted building, and the gray one is the existing building. So these are the formulas that can be used for capacity converting the base shear versus displacement to ADRS format. We are converting this to spectral acceleration versus spectral displacement. Kappa 1 is the model participation. Phi R1 is the roof displacement for the dominant modes. M is the total mass, and alpha is the model mass participation factor. So if you do the calculations for, we convert the spectrum and the curves. So if you do the conversions and calculate the demand, for the existing building, we have approximately 0.1 meter demand from the earthquake. And for the existing building, we have approximately a 0.012 meter demand. And lastly, I want to compare the inter-story drift ratios. The existing building has the blue curve. We have the inter-story drift ratios up to 3%, but retrofitted building has a significantly reduced drift ratio. So technically, that's pretty much I want to talk about. I hope I could cover what I want to achieve. I hope you like what I talked about. And I want you to stay tuned for more webinars, because we are continually doing webinars, conducting webinars every week. So we will have a flat slab design webinar on the 3rd of June. And 24th of June, we have a very special event coming, because we are about to release version 2020 with fantastic new features, actually. So stay tuned for 24th of June. For our users, you can continue to contact us through the support channels. We really love hearing from you. And for those who are new to ProtaStructure, we have very special offers present at the moment. We are backing it with direct technical support and updates, an online help center with webinar recordings, knowledge-based articles, and also we are now launching a pay later campaign. You can contact us through global sales at protasoftware.com or Asia sales at protasoftware.com. As I said, very special offers are waiting for you. So also please follow us through our social media accounts. I'd like to thank you for attention and for sparing 90 minutes of your time. Okay, thank you very much. I would like to end the webinar now. Take care, all of you. I hope to see you again in another interesting topic.